Again, what I want to do in this presentation is, so we saw in the previous one, we were talking about the spherical coordinates, and I referred you to a page in your book where they had a schematic of the polar coordinates and what the polar coordinates translate into from rectangular, or not the spherical coordinates translate into from rectangular to spherical. But what I wanted to show you is the trigonometry behind it. It's actually really just, I think, like I said in the last presentation, just an exercise in right triangle trigonometry. So let me just start like this. All right, so let's say we've got, let's say some point X, Y, and Z in space, okay? Let's refer to, let me get a different color here. The distance from the origin to that point, let's call that rho. Okay, and let's say that the angle that line segment makes with the positive z-axis, we'll call that the angle phi. Okay. All right, so let me drop a couple of perpendiculars here. Let's call this line right here in the xy plane, we'll refer to that length as r. R from the polar coordinates, okay, from the polar coordinates. So that means this would be the angle theta. Okay. And so from right triangle trigonometry in the xy plane now, this quantity right here would be r sine theta. And so this one would be r cosine theta. Okay, how's that look? And then we'll go up here. That's going to be our z. Because again, look at this now. Okay, according to my diagram, notice that the length right here, notice that that distance between the z-axis and the point P, that distance right there with the dotted line, that is actually the same as the length r. So I can actually write like this. Okay. All right, now let's see. Again, from right triangle trigonometry, this would have to equal rho sine of phi. And this side would have to equal rho cosine of phi. And so therefore, that's what this would be as well. Okay, so when you think about it, right, these coordinates here in rectangular form, in cylindrical coordinates, x would be equal to r cosine theta, y is equal to r sine theta, and z is just equal to z, right? We said in a previous presentation that the cylindrical coordinates are really just the polar coordinates with the z dimension added, okay? But in spherical coordinates, how does it translate? Well, r cosine theta is z right here. So we can write, got too many colored pens going on here. So the z I'm going to replace with rho cosine of phi, like that. But we also know from our diagram, again, what does r equal? Here, look, r is equal to rho sine phi. So I can actually write this expression here like this. Rho sine phi cosine theta. And rho sine phi sine theta. Okay, so that's where those three relationships come from. So I'm going to put them down here because this is getting a little messy. All right, so we have x is equal to r cosine theta, but r is equal to rho sine phi. So I'm going to just substitute that in. Y is equal to r sine theta, where r is rho sine phi, again, times the sine of theta, and z is equal to rho cosine of phi. So those are the three equations, gang, that relate the rectangular to the spherical coordinates. That's where those came from. It's just that, like I said, it's just a real nice exercise in right triangle trigonometry. As it turns out, and I think I did mention this before, the spherical coordinates are especially nice if you have something like you have surfaces in space that have a point or a center of symmetry, like a sphere or like a cone, so, anything like that, or symmetry, even symmetry about the origin. Okay, so like as an example of that, right? As an example, suppose that you had the equation of the sphere x squared plus y squared plus z squared is equal to a squared. Okay, well, according to the equations for the spherical coordinates, these right here, I'm going to plug all those in, and I'm going to get the following. Okay, now square everything out. Okay, now notice from the first two terms, these right here, I have a common factor that I can remove, which is rho squared sine squared phi. And when I remove that, I'm going to have cosine squared theta plus sine squared theta. That's my fundamental identity, which is equal to 1. So all of this can be written like this then. Okay. Now, notice I have a common factor again. I can factor out rho squared. And once again, I'm going to have the fundamental identity just in phi this time. And so the equation of a sphere in spherical coordinates is just simply rho equals. Again, look how much nicer that is than this. I mean, that's nice and all, right? That's the equation of a sphere, centered at the origin whose radius is a. But in spherical coordinates, look at how simple that is. Rho equals a. Okay, not too bad, huh? Here's another example. I had mentioned a cone that works well for cones as well. Oh, and by the way, gang, that's one time for all time. Right, so now that we see that rho equals a is the equation of a sphere centered at the origin whose radius is a, like you don't ever have to go through this process. We just did it. How about this one? Now this is the top half of a cone. All right, so what's that going to look like? Well, let's see. If I replace the z with rho cosine of phi, and on the right-hand side, replace the a with rho sine phi cosine theta, squared, of course, plus rho sine phi sine theta. Factor out the common factors. The fundamental identity in theta emerges again. And then when I simplify that, right, so all of this I can replace with the number 1. And then when I take this, the principal square root, I'm going to get rho times the sine of phi. And I can divide out rho from both sides of the equation. And maybe I divide both sides by the cosine as well to get 1 equals the sine of phi divided by the cosine of phi, which is the tangent And we know that the tangent of phi is equal to 1 when phi is equal to pi over 4. So the equation of the cone, which was in rectangular coordinates, z equals the square root of x squared plus y squared, can be found. What this is saying is take the angle phi equals pi over 4. Again, remember, now this is important. Remember we said in a previous presentation, in spherical coordinates, the angle phi is measured from the positive z-axis to the negative z-axis only. In other words, it's measured from 0 to pi radians. Okay, so from the positive z-axis with your protractor, you measure down pi over 4 radians. That's about here. Okay, like that. And there's no stipulation on the x coordinates or the y coordinates. So they can range to be whatever you want. So we then think of, again, we think of this ray right here, this ray that makes an angle of pi over 4, sweeping around the z-axis. And when it does, it sweeps out the cone. Okay, very clever. So the spherical coordinates are especially nice. Like, again, like we did with the sphere. Look at the equation in the rectangular form, right? Z equals square root of x squared plus y squared, which reduces down to just phi equals pi over 4. It's the same surface, it's the same cone, but the equation is much easier. And while we're at it, this business of converting stuff, if you're interested, I'm going to make a remark here, by the way. In cylindrical coordinates, the equation of the cone would become z equals the square root of r squared, which is just r.